Hello. Once again, we're back at our environmental science notes, and you will find that the next few chapters do some quick reviews of earlier chapters, as does this one. You can see the title of this section, this chapter is water. So we're going to begin, and I will go through these first slides quickly, so please be prepared for that. You might remember that the earth is made up of two types of water, fresh water and salt water. Surprisingly, even though we depend on it, fresh water is that which is in the minority, and there is only 3% of the water of the earth is fresh water, whereas 97% is salt water. You might also recall the water cycle, evaporation, condensation, and precipitation. We looked at that in an entire chapter earlier when we looked at the hydrosphere. So we won't say too much more about those, but there is this chart that kind of expresses to you how things happen. Process of evaporation, where the liquid turns into a gas, condensation, the gas back into a liquid, and then precipitation is the fall of that water. Obviously, understanding excuse me. Obviously, understanding the water cycle is critical for understanding what happens with water on Earth. We also made mention of the fact that water can be divided into categories. Sometimes we take a look at what we call surface water, and the title of that certainly gives you the distinction as to what it is: water, fresh water on the Earth's land surface. It's found in things like lakes, rivers, streams, wetlands. And you probably realize the importance of these to human history because throughout history, people have built their cities, their towns on these areas because they needed to have available, fresh surface water handy. River systems are one of these categories. When we talk about a river system, we're talking about the entire conglomeration of rivers that flow into the water. So it is not sufficient to talk about simply, let's say, the Mississippi River system, but you have to backtrack. And you actually can backtrack as far as the hills of that are above the Allegheny River here in Pennsylvania. When you put the whole system together, that whole flowing network of water is what we call the river system. And truthfully, it even includes here, and I forgot to say this, but actually it includes the rain that falls into that. So a river system is a pretty complicated sort of thing to consider. When we take a look at a river system, we want to be sure that we're following it all the way through so we understand, as we trace pollution later on, we want to understand where the pollution originates and where it might end. It's not just a question of looking immediately where you are, but looking beyond that. Another term you heard earlier, as a matter of fact, you had a short, small little project on it, was a watershed. And if you recall from that earlier section that a watershed is the area of land that's drained by a river, page 291 of your textbook gives you a nice picture of that. And they'll show you the different watersheds that exist. And in particular, they highlight the Mississippi watershed because of the fact that it is such a main amount of water in this country. This is the same as the diagram that's in your map on page 291, and this shows you, as I said, the watersheds that are in the world. Probably more than you would think about. You might not realize how many there are, and you notice some of them are quite large. As a matter of fact, here's the Mississippi watershed. And in comparison, there are certainly others like this one here, number 8, which is the Amazon River. Has what seems to be, at least first glance, an area, encompasses an area larger than that of the Mississippi River. So when you talk about a watershed, you need to truly consider all of it and all of the things that go into it. And if you recall your project from before, you might realize that the different life forms that exist there, of course, are based on somewhat temperature and the plants that exist there. But the watershed determines a lot of the plant life, animal life that exists around it and controls that. So that parts of the earth that do not have major watersheds in them doesn't mean they don't have any water, it just means that the water isn't accumulating, it's not flowing from one space. One of the things that we didn't spend a lot of time talking about was groundwater. Again, the term is somewhat self-explanatory. Groundwater is water beneath the Earth's surface. And therefore, we're talking about water that exists in sediment and in rock formations. One of the terms you do need to know is that of an aquifer. An aquifer is simply an underground formation that contains groundwater. And the aquifers are a primary source of water for people in this country. Two of the conditions that affect groundwater are porosity and permeability. And porosity simply refers to the percentage of the volume of rock that has spaces, pores, holes, like you have pores in your skin or the underside of a leaf. You can sometimes see the pores there. And that percentage of the total volume of the rock that has those holes is considered the porosity. In other words, if it's a rock that's kind of spaced apart, you can see some things like that. They almost look like solidified sponges. Then you know that what you have in essence is you're looking at the porosity of it. Permeability, on the other hand, is the ability of the rock or of the soil itself to allow water to flow through it. Obviously, they are somewhat connected, and in your textbook, you'll notice that they deal with those together. Gravel is a good example of something that allows the flow of water through it. So the permeability of gravel is pretty high. Clay, on the other hand, which is very dense, granite is another one, are said to be impermeable. Water cannot flow through those very easily, if at all. Still talking about groundwater, an important concept, particularly when it comes to understanding what happens with pollution, is the concept of a recharge zone. And there's a diagram in your book on 294, 295 that I have on the next slide. But when we're talking about the recharge zone, we're talking about the area of the earth where an aquifer can be recharged, okay? So if you're looking at the picture in your book, you're looking at the layers, and as I said, we'll look at that in a minute. But we're looking at that space where the water can percolate down. Percolate is a term where any liquid sinks through some sort of loose solid. Actually, there are coffee makers through which the water percolates, sifts through, picks up the taste of the coffee bean, and then makes coffee that you drink. That's the same idea. And the recharge zone is very important for what it does. It recharges the water so it's usable, even though it might come down through the earth or down to the earth originally in some polluted sort of form, it still can be recharged to a certain extent. Now this takes a lot of time, so that's the problem, but nonetheless it is possible that it can happen. Wells are connected to the concept of a recharge zone. If you live out in the country, you probably are familiar with the concept of a well. You know, if you go anywhere on the earth and you dig a hole that's deep enough, you're eventually going to find water. And that water is coming from some of the ground underneath, the water underneath there, probably from an aquifer. And that's a good place or good way to find water. Okay, groundwater is more reliable than surface water. If you have a surface pond, you know, it can certainly evaporate. If you go through a spell that's very hot, very dry, or in the wintertime, you may not be able to get to that surface water. But wells provide a way to get to water, and it's a more reliable way to reach water. Okay. Now we're going to continue. Some of this, as I said, was review. Some of it maybe put a different light on some things. Before we do that, here's a look at the recharge zone, and you can see this concept of the aquifer where water is just kind of ponded together. And the recharge zone is here. You notice that there's a layer of porous and permeable rock, and you can even see in the picture how the spaces that exist there. Okay, and then is comparing that to the bottom layer of rock where that layer is not permeable, so the water kind of sits on it. And again, here, if you look at this diagram of the water resting on these levels, you can see why it would just sort of pool up under the surface of the earth. Let's see. I think we can move ahead. Yeah, now, what we get to in this next semester, as I told you, is actually how is water used and how is it managed. Although there seems to be a lot of it, the fact is that we have to be careful how we use all this fresh water that does exist. And one of the main sources, one of the main concerns about using water, of course, is residential water use. Residential refers to where people live. In order for you to use the water that comes through your taps, water has to be made potable, a word you probably should know. In other words, it has to be made safe to drink. And to treat that water, we have to go through a process where we're removing some of the things that are in it, such as lead, mercury, arsenic. And any one of those by themselves are very, very bad. Now, when they build up at any great level, they're going to cause severe health problems, if not death, for people. So obviously taking this stuff out of the water is something that has to happen in order for us to drink it. Water use for homes, for businesses, involves taking out some of the pathogens, besides removing these three elements, for example, also takes out some of the pathogens, some of the organisms, excuse me, the organisms that cause illness or disease, things like bacteria, viruses, worms, parasitic worms. And if water is not treated this way, you could certainly drink it, but you risk getting sick from it. Those of you who are campers, who are scouts, perhaps know that if you go out in the wilderness, you're not likely to just take up some water from a stream and drink it. I believe they have some kind of a pellet or something that would make the water potable, make it safe for you to drink. In addition to the ways that homes use water, we also have to look at the way factories or industries use water. And it's necessary that they have water because in a lot of cases the water provides a way to cool down some of the machinery that's used, to dispose of some of the waste that exists, to generate power, to actually sometimes make the goods that they're making. So water is used by industry. Obviously, the pathogens being in the water do not affect the use of water in this case, so it doesn't have to be treated for an industry to use it. Besides residential and industrial use, we also have agricultural use of water, and this is actually where most of the water of the world is used. You might think it's in your homes, but that's not true. There's a lot of reasons that water has to get used in agriculture so that the plants can grow, but also has to be used so that the way it's used, sometimes certain crops have to be flooded out and made more damp, more moist. And when they do that, of course, the water just sits there, which means some of it eventually is going to be evaporating. The process of providing water to plants artificially is called irrigation. And that gives us ways to water the plants other than direct precipitation. Precipitation, of course, is rain. And you probably know this if you water your plants at home, either some of the plants that you have that landscape your house, or else even if you just take water and go and water your house plants. Maybe I should be doing that today too. But at any rate, agricultural water use takes up most of the water of the world. Okay. So what happens to this? How does this water get into the right places? Well, in this country and around the world, there are several large projects that have taken place where we manage water and it flows. In other words, we take nature and we change it. And those are both good and bad things. In your text, there's a picture on page 299 of an aqueduct that was built in Spain about 2,000 years ago. So this isn't something that's new, although when you look at some of the water diversion projects that you probably know more about, you probably know more about the Colorado River and how that was diverted, and eventually the Hoover Dam was built so that most of the electricity that is needed in the city of Los Angeles is generated from the Hoover Dam, even though it's several hundred miles away. But at any rate, that was done for energy purposes. But dams are also built for other reasons, for example, to control floods. They can provide drinking water for an area where water is scarce, to irrigate plants. As we just said, agriculture takes up much of the water that's needed on the earth. The problem with water diversion, with sending water in different directions, is it sends people and ecosystems out of their places. And it takes up some of the space that they might have lived in and existed in and pushes them aside, literally, because what happens, of course, is now water is being collected and the people and organisms are pushed out of the way. On the other side of the river, farmlands down below the river are also hurt because they might have been accustomed to getting some more water and then suddenly they don't have it. So farmlands are often also hurt because of the fact that water that they had at one time and used is no longer coming to them, and therefore they maybe can't do the agriculture that they had used before. I think I'm going to have to stop because of time restraints here. So let me finish out this section. If you're following along in the textbook, I'm somewhere around page 300. And what that means is we're not quite done with this section, but we'll look at that in the second tape that I do for you now. Thanks so much. See you in a few minutes.